Imagine wood that defies millennia, remaining as solid today as it was thousands of years ago. How does timber survive when everything else crumbles to dust? We're about to uncover the secrets behind wood that refuses to decay. In 2013, archaeologists excavating a well in the Czech Republic discovered wooden timbers from 5256 BC, over 7,000 years old, still holding their shape and strength. You could see axe marks where Neolithic craftsmen shaped the wood. The grain was visible. Cell structures remained intact. This wasn't petrified wood where minerals replace organics. This was actual wood, preserved so completely that dendrochronologists could count growth rings and establish precise dating. Modern pressure-treated lumber lasts 40 to 50 years in ground contact, yet Stone Age timber with no chemical treatment survives 70 times longer. This pattern appears globally, overturning what we know about organic decay. Wood rots because organisms eat it. Fungi break down lignin. Bacteria decompose cellulose. These processes require oxygen, moisture, and moderate temperatures. Eliminate any one and decay slows. Eliminate all three and wood survives indefinitely. The Czech timbers survived waterlogged in oxygen-poor mud. Aerobic organisms couldn't live there. Anaerobic bacteria worked so slowly that 7 millennia barely touched the wood. Cold groundwater inhibited microbial activity further. Environmental accident created conditions where decay couldn't occur. Desert environments preserved through the opposite mechanism. The Tarim Basin in western China contains wooden artifacts over 4,000 years old, preserved through extreme desiccation. Below 15% moisture, fungal spores can't germinate. Bacteria can't metabolize. The wood enters suspended animation. Archaeological sites in Egypt, Peru, and the American Southwest contain wooden tools dating back millennia that look only centuries old. Freezing creates the third pathway. Siberian permafrost has yielded wooden structures over 10,000 years old. Ice cores contain wood fragments hundreds of thousands of years old, locked in frozen time. But environment alone doesn't explain all survival. Some wood persists because humans actively protected it using techniques we're only now beginning to understand. Japanese temple construction employed yakisugi, surface charring of cedar planks. Controlled burning creates carbon layers that, repel insects, resist moisture, and inhibit fungi. Hōryū-ji temple, built in 607 AD near Nara, contains original yakisugi timbers, still sound after 1,400 years. This wasn't decoration, it was engineering that extended wood lifespan tenfold. Ancient Egyptians preserved wooden sarcophagi and funeral boats through dehydration and resin application. Cedar wood forming Khufu's solar barque, buried at Giza around 2500 BC, remained so well preserved when excavated in 1954 that conservators reassembled the entire 43-metre vessel. Egypt's dry climate plus resin coating stopped decay completely. Roman engineers used oak timbers treated with tannin-rich oak bark extract, creating chemical environments hostile to decay organisms. Archaeologists excavating Roman wells and harbours found oak pilings over 2,000 years old still bearing structural loads. Now, the Romans didn't understand microbiology, but they knew empirically that certain treatments worked. Why some wood naturally resist decay involves chemical warfare at the cellular level. Heartwood, dense, darker wood at a tree's centre, contains extractives compounds serving no structural function but defending against biological attack. Teak produces tectoquinone, inhibiting fungal growth. Cedar contains thujaplicins, killing bacteria. Redwood and cypress produce polyphenols interfering with cellulose breakdown. These preservatives work so well that old-growth timber from these species survives centuries in ground contact without treatment. Ice Grand Shrine in Japan, rebuilt every 20 years in Shinto tradition, uses Japanese cypress from trees over 200 years old. Timber from previous reconstructions, some from the 7th century, remains sound enough for reuse. The wood has been active for 1,300 years, cycling through structures, never fully decaying. Modern research, really looks backward. Scientists at the University of Maryland have managed to compress wood while removing lignin, creating a material that's actually stronger than steel by weight, and it resists decay through density. It's a process that mimics the natural formation of petrified wood, but it's accelerated. Meanwhile, Finnish researchers extract natural preservatives from old-growth trees, developing treatments based on compounds that evolution has perfected over millions of years. Understanding why certain wood survives for millennia could honestly revolutionize sustainable construction. Imagine reliable timber with a lifespan of centuries, made using only natural processes, harvesting from older trees with more heartwood, treating surfaces with plant compounds and applying strategic charring. All of this reduces our dependence on toxic preservatives while creating materials that genuinely last. Ancient timber, interestingly enough, also serves as a climate archive. Tree rings record annual growth, which varies with temperature and precipitation. Wood that's been preserved for thousands of years provides climate data that goes far beyond written records. Irish bog oak, for example, trees preserved in peat bogs for up to 7,000 years, has created a continuous tree ring chronology, allowing for precise dating of European climate events throughout the Holocene. This data, in turn, helps us put current changes into context. The oldest verified living tree, the Great Basin bristlecone pine known as Methuselah in California, is, 4,855 years old as of 2025. But, older dead bristlecone wood, preserved by those dry mountain conditions, actually extends tree ring records back over 9,000 years. The wood didn't rot, it waited, becoming this kind of archive of climate, atmospheric conditions, and even cosmic ray intensity through radiocarbon variations in different growth years. What ancient timber teaches isn't just preservation, it's really the difference between engineered obsolescence and genuine longevity. Modern construction, it tends to prioritize cheap materials with minimal lifespan, just assuming replacement down the line. Ancient builders, lacking easy replacement, built for permanence instead. Japanese Miyadaiku shrine carpentry really embodies this. Select the very finest materials, employ the best techniques, and create structures lasting millennia. We live in a throwaway culture treating everything as temporary, yet wooden structures and artifacts have outlasted the civilizations that created them. Hōryū-ji temple still stands. Czech timbers retain their structure. Egyptian sarcophagi protect their contents. These aren't just anomalies, they're evidence that permanence is possible when we choose it. The irony cuts deep. Modern treated lumber uses toxic compounds, chromated copper arsenate, alkaline copper quaternary, leaching into soil and groundwater, creating environmental hazards that, persist for decades. Yet these chemically saturated materials decay within 50 years. Ancient builders, using only charring, plant resins, and careful selection, created structures lasting over a millennium without poisoning their surroundings. The knowledge gap stings. We know more about wood at the molecular level than any previous civilization. We can examine lignin polymers, identify decay enzymes, and even sequence the genomes of wood-degrading fungi. Yet, surprisingly, we can't match what Japanese carpenters achieved in 607 AD or what Egyptian boat builders did in 2500 BC. Our understanding increased, while the results, honestly, diminished. Part of the problem is economic. Ancient builders worked on century timescales. They selected wood from old-growth forests where trees grew slowly, producing dense heartwood rich in natural preservatives. They seasoned timber for years and employed craftsmen trained since childhood. Modern construction, though, operates on quarterly profits. Wood comes from plantation forests, where trees grow fast and young, producing lightweight, resin-poor timber. Seasoning gets compressed, and skilled labor is replaced with chemical shortcuts. But, economics alone doesn't explain knowledge loss. Yakisugi requires no expensive equipment, just fire and technique. Resin treatments use naturally available materials. Tannin extraction comes from oak bark, which is actually a waste product of timber processing. These methods are low cost and low tech. What they really require is patience, care, and, a cultural commitment to longevity over convenience. Some knowledge persists. Japanese temple carpenters still practice yakisugi. Scandinavian boat builders still use pine tar methods dating to the Viking Age. These aren't museum demonstrations. They're living traditions producing functional results. Yakisugi-treated cedar in Japan outlasts pressure-treated pine in America by decades, using only controlled fire. The question isn't whether we can build for permanence. We can. The evidence surrounds us in wooden structures surviving millennia. The question is whether we'll choose to, whether we'll value longevity enough to select proper materials, employ proper techniques, and accept that quality takes time. The wood that wouldn't die teaches a lesson we've forgotten. Permanence isn't about technology, it's about understanding natural principles and having discipline to apply them. It's about selecting materials wisely, treating them properly, and building with future centuries in mind rather than next quarter's profits. If this exploration revealed that longevity comes from respecting natural limits and choosing quality over convenience, subscribe to Through Time. Share this with someone who needs to understand that materials don't have to be temporary, and that sometimes the best solutions come from rediscovering what worked for thousands of years. The wood that wouldn't die is still teaching, if we're willing to listen.